All right, in this last lecture, we're going to talk about, as I promised, Karnaugh maps, which are a very simple technique for optimizing your circuit design. That is, by minimizing the number of gates, not to a true minimum, but reducing, I should say, the number of gates that you're going to have to use to implement a particular truth table and expression. So let's imagine this very simple, and it doesn't matter what the output here, but imagine I have 4 in. So how many rows do I have with 4 in? 2 to the 4, which is 16. And I have one output, which is E here, and I've just color-coded it slightly different. Okay, so we could do what we've been doing up until now. We could identify all of the ones here. There's one there, et cetera, et cetera, et cetera. Build the sub-expressions from these 4 inputs using AND and NOT, combine them with OR, draw the circuitry. But you can see this is going to get to be a fairly large circuit. But let's just go ahead and pump through that as a good reminder, and then we're going to see how we can do a little bit better. All right. So what are we going to do? Again, we're going to go down through the output and isolate the ones. There. Okay, and we're going to build the sub-expression. So let's build the first one. You go back to the input, not A, B, C, not D. There it is right there. Let's go to the next one. What's the sub-expression? A, not B, not C, not D. Good. That one, there it is right there. Now let's do a couple more just as for practice. I've got what? A, not B, not C, D. All right, that's pretty easy. Let's do another one. A, not B, C, not D. And now I think we can probably just go ahead and do the rest. Okay, so just convince yourself that those all map back to those sub-expressions. So, okay, so we've got a bunch of noddings, we got a whole bunch of AND gates, and of course I can combine those with an OR gate, and we can keep through that process. Okay, and you can see that there's a fair amount of circuitry. All those AND gates, all those little dots, corresponds to a gate which corresponds to 2 transistors. I'm going to have ORs to combine all of these. Those correspond to 2 transistors. And as I said earlier, it'd be nice if we could try to reduce the amount of gates and therefore transistors and therefore the amount of space on the underlying circuitry. So what I'm going to do is the way these Karnaugh maps work, there it is right there, Karnaugh, that's how you spell it, is they reimagine the truth table. Okay, and the way we're going to draw this truth table is instead of having each entry for the 4 inputs take a single row, we're going to have them occupy this little 4x4 matrix. So notice what I have up here. Up top, I have the input pair AB, and on the side, I have the input pair CD. So this entry corresponds to when A is 0 and B is 0. A is 0, B is 1, A is 1, B is 1, and A is 1 and B is 0. Okay? So, and then this, of course, corresponds to what C and D is. C is 0, D is 0, down to C is 1, and D is 0. And notice, by the way, that there's no loss of information. This is 4 by 4, which is 16, which is how many rows I have. So each cell here corresponds to a row. So it's simply a different visualization of the standard truth table. And so how do I populate it? Well, for any cell here, I know what row it corresponds to. So for example, well, let's do the cell. This cell is A is 0, B is 0, C is 0, D is 0. That's that row right there. This cell is 1, 0, 0, 0. So that must be this one right here. So there is a direct translation. Every row here, in particular those outputs, gets shoved into here. Now obviously I need a different one of these for each of the outputs. This is only for one output, okay? All right, so let's go ahead and just start populating it. All right, there's 0, 0, 0, 0. I know what the output is 0, so I put a 0 in this now. Let's call it a 2-dimensional truth table. Let's do this one. 1, 0, 0, 0. That's this row right there. There's a 1, so I put a 1 right there. Let's do a few more. So this corresponds to 1, 1, 1, 1. Let's see. There it is right there. And I've put a 0 here. By the way, notice the ordering here. I've got 0, 0, 0, 1, and then I've got 1, 1, and 1, 0. That ordering matters. You have to do it in this order, and I'm going to explain in a little bit why this ordering matters. Okay? But until I do that, notice that this bit right here, the second 0 and the first 0 are the same. The second one and the first one are the same. The second one and the first one are the same. That's not an accident. And the same, of course, is true here. We're going to take advantage of that structure in a minute. All right, let's do one more. 0, 1, 1, 0. That corresponds to, let's see, 0, 1, 0, 1. that, oops, sorry, 0, 1, 1, 0. 0, 1, 1, 0, that's a 1. So I'm going to put a 1 right there. Okay, good. So I can go, there's a direct mapping from this one-dimensional truth table to this two-dimensional truth table. And all this information is here. This is exactly what I want. I want the circuitry to be 1 for these inputs here, 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 and here, and at 0 everywhere else. Okay? So how does this help me? All right, well, let's look at a few things here. Let's look at this string of 1s right here. Okay, so remember, again, conceptually, what do I want? I want to build some expressions that evaluate to 1 here, here, and here. And if I can do that, I'm home. Then I've implemented this computation that I've specified in the truth table. Look at this expression right here. Okay. Well, let's see. For a 1 to be here, do I care what the value of C or D is? No. Because notice, no matter what pairs of values C or D are, this thing is a 1. Right? And in fact, it's a 1 when A is 1 and B is 0, no matter what the value of C and D are. Ah, that's interesting. Okay. So what that means is if I have this little expression right here, A not B, how did I get that? A not B. So when A is 1 and B is 0, which means that AND is 1, I want a 1 on my output. I don't care what C is. It's completely irrelevant to me. Yeah. So notice what I just did. A single sub-expression with 1 AND and 1 NOT gave me 4 rows of my truth table. That's incredible. That's incredibly efficient, right? And I did it because I've noticed this pattern, and of course that's because I've put this in this nice little two-dimensional truth table, is that these 4 1s don't depend on C and D, and all I care about is then that value right there. So there's a big bang for your buck. I've gotten 4 1s out from a single sub-expression with 1 AND and 1 NOT. Very nice. All right, so now what do I have to do? I still need, remember, all I've got to do is build an expression that evaluates to 1 that occupies all of these cells right here. So once I get those covered, I've got, and then I can start building my circuitry. All right, so let's look at this one right here. So there's 2 1s next to each other. And let's see, so it's not quite as clean as here. I can't just ignore A, B, or C, D. It still depends on both of them. But what do I know here? What doesn't matter? Let's put it this way. Well, there's a 1 here and here when what is true? Well, when C is 1 and D is 0. So that's clear, right? Where we have to be in this row of the two-dimensional truth table. Now, do I care what the value of A and B are? Yes, because it's not a 1 across the whole thing. It almost is because I had a 1 here, but I don't have a 1 there. So if I had a 1 here, then I'd have that same win. I'd get them all. Yep. But what don't I care about? Well, let's see. A is 0 here and A is 1 here. Those are the only 2 possible values. So in fact, these 2 1s right here don't depend on A, and they only depend on B equal to 1. So let's see what it is. When C is 1 and D is 0 and B is 1, then I get those 2 1s right there. Nice. It's not quite as much of a big as a bang as you got here, but it's certainly saving something. So when B is 1 and when C is 0 and B is 1, C is 0 and D is C is 1 and D is 0. So B, C, not D. That little sub-expression evaluates to 1 in these 2 situations. So again, one sub-expression with only 3 variables, by the way, because A is irrelevant here, gives me 2 1s. Nice. All right, so we're almost home. We've just got to cover those 2. Okay? So I could do the same trick. I could draw a little colored box right here, and what would be true? A would have to be 1 and B would have to be 1, and what else is true? I don't care about D, because D can flip between 0 and 1. So I could have written another expression that was A, B, and not C, and I would have gotten those 2 right there. But it turns out we can do a little bit better. So let's think about not just those 2, but these 4. Okay? So notice that they're overlapping with the previous one. We'll get back to that in a little bit. All right, what doesn't matter here? All right, but what do I know? I know that in order to get these 1s here, C must be 0, right? C can't be 1. And I also know that A must be a 1. So think about that thing. C equals 0 carves out rows. A equals 1 carves out these two columns. The intersection is that little square. So these 4 ones right here don't depend on B, because B can be 1 or 0. They don't depend on D, because that could be 0 or 1. And the only thing I care about is when is A 1 and when is C 0. And what's that as sub-expression? A, not C. Now notice that this sub-expression, let me put them all up here. This little sub-expression, A and not C, will evaluate to 1 in these 4 instances. This little sub-expression here, A not B, will evaluate to 1 in these 4 instances. There's an overlap. Do I care? No, what do I care? So let's think about this situation right here where A is 1, B is 0, and C is 0, and D is 0. So what's going to happen in our expression here? This will evaluate to 1, this will evaluate to 0, and this will evaluate to 1. Great, 2 and 1, I only needed one of them, but what do I care? I'm going to get a 1 at the output, and it doesn't matter that these two sub-expressions both said, yes, I'm here, because it's irrelevant to us when we OR. As long as one or more of them is 1, we're still going to get the same answer. So you're allowed to overlap these things. And what's the benefit of overlapping? Why did I overlap? Is, well, the sub-expression was easier. Simpler, it's shorter. I only have 2 variables instead of 3 variables the way I did over here with this one right here. So notice what happened now. By simply drawing this Karnaugh map, this 2-dimensional truth table, I was able to take, well, let's go ahead and look at the comparison. These sub-expressions here, right, and then of course I have to combine them with OR, and I could reduce them to those 3 little tiny sub-expressions. And so the amount of circuitry, the amount of gates, is greatly reduced. Now, the Karnaugh map are really just one of many, many different techniques for doing optimizations, and in fact reducing the number of gates and transistors is only one of many optimizations you have to do. You also have to think about where are things positioned and how much power and lots of complexities in designing circuitry. But what I hope that you got out of this from the very beginning of when we started with binary numbers, through Boolean logic, through gates, through transistors, and eventually circuit design is an appreciation for the nature of computation. You now know the building blocks of a modern day computer and how we can do actual computations. And there's a certain simplicity and beauty to it, and a remarkable complexity to actually get it working. And I hope someday you'll be able to take a computer architecture course and learn some more about it. All right, that's it for now, and that's it. This is the last lecture. We'll see you live in a little bit, and we'll talk some more before the class ends, though. Talk to you soon.